Okay. So I'll start. Okay. Good afternoon, everybody. My name is Misha Kazhdan. I'm a professor here at Johns Hopkins University. What I want to talk about is sort of this general area in computer graphics called gradient domain processing, and a little bit sort of my interest in the area, specifically sort of the transition from doing things on images to doing things on surfaces, on triangle meshes. Okay. So what's the general idea? If you were asked, how do you think of representing an image? You would probably say it's a two-dimensional array. At every point, you store something called a pixel, right? So it's a width by height array, and it stores color values. Great. This is nice. It's an easy way to represent an image, which is something we're familiar with, 2D arrays. That's fine. But it's not how we tend to view the world. It's not how we interact with the world. And so maybe it's not actually the right representation. That's sort of what gradient domain processing is talking about. Maybe we want to represent images in a different way to enable some of the processing that we do as humans. Okay? And it turns out that if you represent images in a different representation, a lot of tasks become easier. And here's a list of a couple of them. I'll show a couple of examples, hopefully convincing you that this is in fact very easy, very nice, very simple. Okay. So what's the idea? The idea is, instead of representing this as a two-dimensional array of pixels where, at the ijth position, you have the color at that position, maybe red, green, and blue values, maybe 24 bits, maybe 32, I don't know. Maybe you're doing hyperspectral imaging and you're trying to figure out how, birds see the world, whatever, you have some value at each pixel. Instead of doing that, what we're going to do is we're going to store values not on these cells or at these pixels, but at edges between pixels, these horizontal and vertical edges. So, at the ijth edge, we'll store, or ijth vertical edge will store the difference between the value of pixel ij and the value of pixel ij plus 1. We'll also store values at horizontal edges, which store the difference between horizontal pixels, neighboring horizontal pixels. That'll be our idea. And the reason is that this is actually sort of more in line with how we see things. We don't tend to see absolute color. What we tend to see is abrupt shift or changes in color. And that's something that's nicely captured in this difference along an edge. It tells us how, is there a shift between neighboring pixels? If two pixels have roughly the same color, then the gradient value or the value along that edge should be small. If there's an abrupt change, there's some sort of boundary in the image, we expect a large difference, positive or negative, depends on sort of how things are changing. We're expecting a large difference along that edge. Okay. Let me try and explain why this representation, this gradient domain representation makes things easier. Suppose you go out and you take a picture. This is a picture I took, I believe, in Haifa. I set my camera up on a tripod and I turned it around and took multiple pictures. And what you're seeing here is sort of the coverage. This is sort of a false color representation of the coverage. So when things are in the same color, they come from the same camera. And you can see that sort of there are many different images that were used, or pictures that were used to composite this large panorama. The problem is that as my camera pans around the scene, I have some of the settings set automatically to adjust for how bright or dark it is. And you can see these discontinuities as the parameters change, right? So as I go from this image to this image, this was exposed for a little bit longer. This is exposed for a little bit shorter because this was a little darker. This was a little brighter. And so at the edges, we're seeing this discontinuity. So we want to fix this. This is a classical problem in panoramic image stitching. How do we do that? Well, if we think about what's going on in the gradient domain and we look at this image, what we can say is, in the interior region, like somewhere in here, everything is really good. The gradients are fine. What's wrong? What's wrong is the gradients that go from one image to the other. Here we're seeing sort of large gradient values indicating some sort of abrupt shift in color values, but we don't want it to be large. We want it to be continuous. Well, fixing that is actually very easy. Just sort of set those differences, those horizontal or vertical edge values, to be 0. That tells the image that there shouldn't be a change as we switch from tile to tile. You do that and you get an image that looks like this. Okay. Here's another example. Let's say you take your camera and it shoots not at 8 bits per channel, but maybe at 16 bits per channel. So you have an HDR, high dynamic range camera. That's certainly something that you get now. So you get this really nice image with a lot of dynamic range. The only problem is that your monitor is still 8 bits. 8 bits per channel. How do you represent it? How do you represent this image? Well, so the simple thing you could do is, you can either sort of look at part of the dynamic range, or you could scale the dynamic range so that multiple colors compress into the single one, but you won't get all of the visualization here. For example, sort of I'm exposing this high dynamic range, or trying to visualize it as though I'm trying to see the parts that are really dark. The problem is that things that were bright get oversaturated. I can try and see the things that were really bright. As a result, the things that are dark are invisible. I would like to see everything. How do I do that? Well, this turns out to be not hard. Again, in the gradient domain context, right? What do we want to do? We want to get a new image, and we want to preserve the boundaries, the information about how colors change. Okay. But what we don't have to do is we don't have to preserve the magnitude. We just need to hold on to the concept of there being an edge, a transition from one color to another. We don't necessarily have to hold on to the magnitude of that transition. And that motivates this very simple approach, which is take your HDR image, your high dynamic range image, represented in the gradient domain. What's going to happen is you're going to have some edges which are large. You're going to do a sort of have a large change in value. Dampen that a little bit. Just scale it down. Don't set it to 0. But make it a little smaller, so the edge is still there because you're preserving the difference, but don't make it quite as extreme. As a result, the total dynamic range of your image will go down, but you will still preserve the edges. Okay, and so you'll get an image maybe that looks something like this. So this is a realization or visualization of this sort of high dynamic range to low dynamic range transformation, HDR to LDR. Again, just all you needed to do in the gradient domain processing is just look at this representation in terms of values at edges, see where they're big, and dampen them if they're big. Make them a little bit smaller. Still preserve them so you still get details like, you're going from shadow into light and so on and so forth, but just so that they're not so big so that they don't sort of use up as large a dynamic range. Okay. Good. So that's sort of gradient domain processing. What interests me is the question of how do you do this? How do you take this technique that we understand for images and push it to the context of surfaces? And what does that even mean to do this on surfaces? So that's what I'd like to talk about today. Before I jump forward, let me ask if there are questions. Unless, Sudha, you want me to hold off until the end. You tell me.
No, sounds good. We can definitely take questions.
Okay. All right. All right. So what's involved in this? Well, we have to do a little bit of mathematics. But it's not going to be so bad, right? We have an image, right? And we have some description of what we would like it to look like. And what we want is we want two types of constraints. We're going to say we're looking for an image F, and it has to satisfy two properties. One is it should look like image G. So there's some energy which says how different is image F from image G, right? We're going to integrate, or we're going to sum over all the pixels. We'll look at the square differences. That's one constraint. The other constraint is telling us, how different is the gradient of F from some target prescribed vector fields. That's sort of what we were looking at before, where we would prescribe the differences and we tried to fit a scalar function to those. And what we tend to want to solve is some sort of balance between these two. We want to match the values of G and match the changes represented by V. And there's this alpha term that sort of says, how do we trade off between these two? Okay, so this is an optimization problem. If you look at what's involved, this is a quadratic problem in the values of F, and it turns out that there is some linear system that you need to solve. The linear system I've written out here, that will look like this. If you can solve this linear system, you will get the solution F that optimally matches or minimizes this energy. Now, what's going on in this? What are these terms? We have this guy over here. That's called the Laplacian. It's really just you have a pixel, you look at its neighbors, you look at the difference between the pixel value and the average of its neighbors. If the pixel values nearby around you all have the same color, then the average is going to be the same as yourself. That'll be 0. If you're sort of brighter than your neighbors, then you'll have a positive value. If you're darker than your neighbors, you'll have a negative value. This is often used as some sort of edge detectors. So if I take this image F, right, and where the color is roughly uniform, let's say over here we have roughly uniform, we're just going to get a gray color. If we look at somewhere where there's a boundary, we will get to sort of this double contour, bright and dark. And the reason it's bright and dark is because on one side of the edge, you are darker than the average of your neighbors. On the other side of the edge, you are brighter than your average of your neighbors. They tend to come in these black and white pairs. Okay, so that's this Laplacian. And the other thing you need is a divergence. The divergence says if you have a vector field represented over here, is it all coming into one place? Is it coming together? Is it converging? That's represented in black over here. Or is it diverging from a particular point? So these guys over here are all diverging. So this is bright over here. Or it's neither diverging nor converging, in which case you'll get some great sort of gray values over here. So these are sort of the mathematical constructs that we need to work with in order to be able to realize, to solve for the gradient domain problem. So, I said it's really easy to solve it, to sort of solve these problems in the gradient domain. And it's almost true in the sense of you can find the gradients that sort of describe the solution you want, but then there's still the problem of trying to find the image that actually realizes those gradients. That's what this equation is giving you, sort of how do you solve for it? Okay, and it turns out it's a linear system. And what we're going to want to do is we're going to want to solve exactly the same thing, exactly the same type of equation. It's called the screen-Poisson equation, but now on a mesh, a triangle mesh. Okay, so we have vertices, they connect together in triangles, triangles share edges, and so on and so forth, but we have the same type of equation. So we need to interpret these concepts, these sort of quantities over here that we saw for images, we need to interpret them on a mesh. Okay, so the first thing is, where do things live, right? You have F and G, that's a signal, that's some sort of value, maybe it's a color value. A natural place to do this is to store the values at vertices. So that's where we're going to store them. So we're going to have samples, discretely sampled values of a function stored at the vertices. Great. Okay, we have a vector field V. Now, a vector field should lie on the surface, or in math speak, it should be tangent to the surface. Well, if you look at a triangle mesh, there is no well-defined tangent place at vertices or at edges, but there is on the triangles. The triangles are flat objects, and so naturally there's a plane that passes through them. So we can talk about vector fields, vectors that live in that plane. So we'll associate a tangent vector to each triangle. We have this notion of a mass matrix. Beforehand, when we said, we wanted F to be similar to G, it didn't make a difference which pixel you were looking at. They all kind of look the same. That's not true when you're looking at meshes. The different vertices, some belong to bigger triangles, some belong to smaller triangles. So when we say that the value of F should match the value of G at this vertex, we need to say how important is it that they match based on sort of the area subsumed or occupied by that particular vertex. So that is this one thing over here, which was just the identity before, is now what's called a mass matrix. So that incorporates the notion of how heavy every vertex is. How important is it that they match? You have the Laplacian before so previously it just said, it's the difference between you and the average of your neighbors. But now if you're at a vertex, your neighbors might not be uniformly distributed, either in terms of angles or in terms of distances. So you need to take into account how things are distributed. And it turns out that there's this nice matrix that still gives you the average, the difference between you and the average of your neighbors, but now the average is weighted based on how your neighbors are distributed. This is called the cotangent Laplacian. Also well understood. And then finally, there's this divergence operator. It's kind of related to the gradient and to the notion of area of a triangle. Again, computable, not particularly hard, reasonably well understood in the geometry processing world. The key point is that all the constructs, all the operators needed to define this linear system are well defined and exist. Okay. The one thing I'll sort of point out, in case I have a chance to get to it later, is, to do this, to define these linear operators, the mass, the Laplacian, and divergence, we needed to know, really all we need to know is the notion of the lengths of the edges of the triangles. If we want to figure out the area of a triangle or the angle of at a vertex in a triangle, we can do that just knowing the edges. This is sometimes called the metric. Typically, if you have a triangle mesh, you have the vertices live in 3D, you can take an edge, which is two vertices, you can look at how far apart they are in 3 dimensions, and that gives you this notion of edge lengths. That's sort of the standard way to do that, but it doesn't have to be that way. You can just describe sort of abstract notion of lengths that are not realized by any embedding. That's perfectly fine. Okay, so let's take a look at what we can do with this. So again, you have a collection of images in 2 dimensions. You took them, your camera parameters change as you move from image to image. You somehow manage to align them, which I'm not talking about today, and you get these seams. Right? You want to get rid of them. Again, what are you going to do? You're going to create this target vector field, V. It's going to be equal to the gradients in the interior, but across the seam, it'll be equal to 0. Okay. You solve this optimization problem, you get this nice seamless image. Same thing happens for surfaces. So you have 3D scanners and you take an image, or you take a scan of an object that might be on a rotating table, and you have a laser range scanner, and you take scans of it, and you get this 3D geometry. Typically, in addition to the geometry, you'll also get color information. You'll also have a color camera there as well. And so you get colors from the different perspectives as it's on the turntable, and you can try and align them. And again, because of changes in perspective and camera parameters, you take the images, you can sort of map these onto the surface, but you get these discontinuities as you shift from one image to the other. Do exactly the same thing. You copy the vector field from in the interior, you set it to 0 across the seams, you solve the associated linear system, you get a nice seamless texture on your surface. Here's another example. So this is a little bit more general. Let's say we have an image. And what we want to do is we want to find a new image F that sort of matches this guy, but whose gradients are some scaled version of the gradients of this guy. So for example, if I want the gradients amplified, if I want beta is equal to bigger than 1, what I'm going to have, right, I'm going to solve this screen Poisson equation. I want F to match the input image and the gradients of F to match the scaled gradients of this input. And when it's bigger, so I want the gradients to be bigger. That means that sort of I want it to be sharper. I want more change. This is a way of sharpening images. This is a classical way for sharpening images. If you see images online, you see this sort of little silhouette over here. This is caused by some sort of overshoot in this process where you sort of want to change too big and then you have to come back down because you also have this constraint over here, and it plays a balancing act. And if you see these halos, that usually means that you're seeing something that's a result of this type of gradient domain sharpening. We can do this also on surfaces. If I have a signal on the surface, I can ask for another signal that on the one hand looks similar to it, but whose gradients are amplified versions of it. If I make beta bigger than 1, I will make it sharper. If I make beta less than 1, maybe 0, then I get a smoother image. So I can do image smoothing. In fact, as I let beta go to 0, this is a very classical notion of smoothing called heat diffusion. What's more interesting to geometry processing people is that when you have a mesh, you already have a function at a vertex. You have the function is the XY position, Z position of that vertex. So you can actually do processing directly on that, on the embedding of the surface. Right? And if you do that, you can either sharpen the geometry or you can smooth the geometry. In fact, if you sort of repeatedly smooth this geometry with a little bit of cure, you get something that mathematicians call as mean curvature flow. It's very nice. If you adapt it a little bit, you get actually something nice, something called modified mean curvature flow that takes surfaces or spherical surfaces and actually maps them, evolves them into spherical geometry, evolves into a sphere. So you get this canonical mapping over a spherical domain. It allows you to do parameterization and cross-matching and all sorts of data transfer. Good. So we saw this example. You want to do smoothing, so you're going to set beta is equal to 0, and we had this alpha term that sort of says how much do we want to fit the original surface? How much versus how much do we want to sort of match the target gradients? Turns out this value alpha doesn't have to be constant. It can itself be spatially varying. So I can ask that there is more interpolation where I think there's detail, so I do less smoothing, and less interpolation, i.e. more smoothing, where there isn't detail, right? And so I can get edge-aware smoothing, which is a very nice process. So for example, I had this image over here, and I want to preserve the details around the eye. If I just do generic smoothing, I'll lose these details. If I do smoothing that's aware, where I sort of have a larger interpolation value because I can sense that there's some sort of detail over here, then I get some sort of smoothing that preserves that. Let me pause for a moment and just ask Sudha, do I have time? How much time do I have?
We still have time, around 10 more minutes.
10 more minutes. Okay, then I will keep going. Good. So another application, and this is going to appear completely unrelated. Well, it turns out that if you think it's unrelated, you're wrong. But it's not obvious that it's related. It's this problem of vector field visualization. So oftentimes when we're running physical processes, we have a description of what's happening as a vector field. Maybe it's describing, the wind or the fluid flow, or the aerodynamics as air passes over the wing of an airplane, something like that. We have a vector field in space that describes it. We'd like to be able to visualize it. So you could visualize it like this. This is a little awkward. So Cabral and Leadham 2 decades ago came up with this approach called line integral convolution. The idea is start with just totally random image, okay? And then if you want to sort of visualize this vector field, what you're going to do is you're going to pick a point and you're going to change its color. And the way you're going to do that is you're going to follow the vector field, right? So if I'm over here, I would have been over here. I'm going to follow the vector field around forward, and I'll also follow it backwards, and that'll trace out some sort of path. And what I'll do is I will replace the color value over here by the average value along this path. And what's going to happen is if a point is over here, mostly it's on the same path. So it'll look like it has the same color. And so what we're going to have is this visualization of the vector field, which looks like these sort of smudges that are traced out along the flow. Okay. Now, we could do this on meshes. This is possible. It's very hard. And by hard, I mean not mathematically hard, not even implementationally hard, just painfully slow. So we don't want to do that. So what we want is something else. We want to look at this as a different type of problem. Okay. Okay, so if you recall, if we wanted to do smoothing, one way to do this is we'd say, well, we want to solve for the image on the one hand that matches this guy, on the other hand, whose gradients are as close to zero as possible, right? This beta term should be equal to zero. We want to dampen the gradient. So that's the system that we would like to solve. Okay, and that gives us smoothing. That's isotropic smoothing. What happens if we want to do smudging, anisotropic smoothing? Let's say we have this vector field that points up, and we would like to smooth just along the vertical direction. How do we do that? Well, it turns out you can play geometric tricks. You can take your patch of surface or your patch over here, your image over here, and just stretch it out. And in this stretched out domain, just do isotropic smoothing. There you go. So you just smooth it. And now compress it back. And what's going to happen is these circular regions, these isotropic regions, blurry regions that you see in the bottom, will collapse down into thin ovals, something like that. And now what you're getting is exactly what you wanted. These smudgings, as it were, this sort of blurring that is aligned with the vector field. So how do we do this for surfaces? Well, what we'd like to do is we'd like to take the surface and stretch it perpendicular to the direction where the flow is going. I don't know what that means to stretch a surface, but luckily we don't have to know what that means, because if you recall, we talked about sort of this notion of this metric structure on a surface, and it's just about assigning edge lengths. We don't actually have to embed the surface so that it realizes them. I don't know how we would do that, but we don't have to. All we need to do is change the notion of edge lengths to say, this edge that is perpendicular to the direction of the flow should become longer. Okay, that's all we need to do. And then in that context, we're going to do this anisotropic blending. And we're done. So here you go. Here's a surface. You have some sort of vector field defined on it. You're going to start off with some random signal. You're going to stretch the metric perpendicular to this direction. So, the distance from here to here suddenly seems much larger than it used to be. You can do smoothing in that domain. And what you're going to get is sort of these nice flow lines, this nice visualization of line integral convolution realized as sort of gradient domain processing. Okay. So what did we do at the end of the day? We said, if you can take these sort of basic operators from multivariable calculus, differential geometry, whatever you want, Laplacians, divergence, this mass matrix, if you can take them, it becomes reasonably straightforward to take techniques that we know from image processing and transform them to geometry processing, to do stuff like gradient domain processing, line integral convolution, and many, many other things that I didn't talk about today. What's nice is that these operations are actually well understood. There's some really smart people, not me, really smart people, mathematicians, geometers, what have you, who have worked on trying to define good notions of these operators on meshes. So they sort of done the hard work for us. After that, we can just take these concepts that are well understood for image processing and carry them over to geometry. So what's nice, what do we learn as we look at the difference between working with images and working with geometry? Images are nice. Images are very regular, right? If you have a pixel, you can ask, who are my neighbors? It makes it really easy to do all sorts of nice calculations. You get this regularity. You can leverage that to do parallelization, out of core processing, multi-resolutions, fast Fourier transform. All that's realizable because of this regularity of the domain. On geometry processing, you don't have that. You have these triangles, some triangles, some edges have long lengths, some edges have short lengths. Sometimes the angles are big, sometimes the angles are small, and you have to deal with it. Before you can do anything, you have to figure out how to deal with it. And just getting off the ground and running is hard. But if you can figure out how to do that, you can do some really interesting things, right? So you can do stuff like, do this anisotropic processing, right? Because all we do is we change the notion of edge lengths. Since we sort of didn't require the mesh to be uniform, we can make it to be more or less uniform in whichever preferred direction. All these operations that we sort of saw, like line integral convolution, they become just as easy as anything else. So there is a startup cost in doing geometry processing, but once you're through that, you can actually do a lot more than you could do with image processing. So that's sort of what I found is pretty cool. So that's it. That's all I have for you guys. Happy to take questions if you guys have them.